Hello. In this lecture, uh, we will discuss about analogous system. In the previous lecture, we have discussed the uh, two kind of systems which have been modeled by some differential equations. One was electrical system, and number two was mechanical system. Right? These are the two systems we have developed. And what you have learned from here that the basic elements was R, L, and C, and in this case mass, spring, and damper. These are the three basic elements, and you see in both the cases there are the three elements which actually the qualities which describe the system in all. Right. So here we will see what is the relation between the two systems, and in the previous classes also we have discussed this corresponding a second order system, and this also corresponds to second order system. So definitely there is some analogy between the electrical circuit and the mechanical circuit, right? So electrical system network, or whatever you call it, electrical system and mechanical system, so there must have some analogy. So once there is an analogy, that means similarity between the two systems, and you see this is electrical system is second order and mechanical system is also second order. That means the differential equations are of the same form, right? But actually we get differential equations of same form. First conclusion again true. Differential equation is of same form, right? Second thing is that here also you are getting the three elements, here with the three elements. That means the similarity of parameters. So there will be the similarity of the parameters. So once you get the similarity of the parameters as well as the same kind of differential equations, so one system is given to you, you can get the corresponding another system, right? Say for example, mechanical system is given to you in terms of mass, spring, and damper. You can draw or you can get the differential equation corresponding to that mechanical system in electrical network, right? So that is the purpose how the analogous system of this lecture is that how the analogous system corresponding to the mechanical system in electrical network can be constructed, right? So first of all, there are the two terminologies. One is known as force voltage, AV, and number three is force current, FI, terminology for the analogous system. That means why this force voltage and force current? That is definitely a reason why. Why? Because you see, in any mechanical system, what is the forcing function? That is force. And in mechanical system, what is the forcing function? Either voltage or current, right? So that is why we can say this is a force voltage or force current analogy, right? So mm, uh, in order to get uh, the equivalence of the two systems, that means the whether the system will be analogous or not, that means if RLC is given, how the R will be replaced by, and which will the R, and that means is there any relation between RLC and MKB, like R may be equal to M, L may be equal to K, C may be equal to P, not like that, but definitely there is a relation between these set of variables, right? So let me just try to find out what is the relations between the two sets of variables in electrical network and mechanical network. Then you can get why this is called the force voltage and why it is called the force current analogy, right? So let me discuss that first. So mechanical system, we will make it fixed. This is your rigid surface. Say this is your maybe spring, maybe this is your damper, and this is your mass M, right? So this is your mechanical system, and corresponding to that you get xs by fs. X is the displacement of the mass with respect to its equilibrium positions. Already we have derived this is ms square plus bs plus c, sorry, k. Or in terms of differential equations, but you write m d2x dt2 plus b dx dt plus kx is equal to f. Right? Now we will write two types of equations in case of uh, electrical network. Right? We will discuss about the electrical system here. So first of all, we will consider a series RLC. See, this is your VI voltage source you are applying here, and this is C, and here you want to get the output voltage across C. So what is this? This is IT. IT is the current flowing through it. And if you analyze this network, so we get the differential equation from this form, such that you can get the analogy between the electrical system and mechanical system. So what we have to do, we have to write the KVL as here this is the voltage source here, so you have to use the KVL, right? So what is the KVL corresponding to that? You see it RIT plus you see L didt plus 1 by C idt is equal to bit voltage source. This is the differential equations of the this series RLC circuit. This is a series RLC circuit, right? Now this is not the differential equations, because once we have to get the differential equations, that means all the terms must be in terms of differentiations, right? So here is the term idt, see, and how can we get the differential equation corresponding to that? That can be possible if you consider this current I is nothing but rate of change of charge, but Q is the charge, right? You know the relations. I is equal to, that is the current flowing through any circuit is equivalent to rate of charge of that circuit, that is the dq dt. So now I dt, what you get, I dt integration is equal to dq, that is the total amount of charge. This is the total amount of charge. So you can just modify these equations, like you can write it like R it plus bit dt plus 1 by C into Q is equal to bit. Right? Now you see, this is, there is no integration term, right? So if there is no integration term, and it will be replaced by say dq dt. So you can rewrite this term as R, instead of it we write dq dt, right, plus ddt of it. So ddt of dq dt plus q by c is equal to bit. Right? So if you just write these equations in terms of highest order to lowest order, so what will get ddt of dq dt? What is this? That means d2q dt2 plus r dq dt plus q by c is equal to bit, or you can say it bit, right? So you see, these are the two equations. Is there any similarity, or you missed something? Sorry, this is L didt, so this will be L, this will be L, right? So you see the similarity. What is the similarity? First of all, this is your forcing function F, this is your forcing function B. That means this circuit and this circuit, that means electrical circuit corresponding to the mechanical counterpart, will give you the force voltage analogy, right? And these two are, these are the two equations which are the second order differential equations of the same form. And you see, Here, in case of mechanical system, what is the output? X, right? Here, what is the output? I can say it as your charge. That means when the force voltage is given here, that means the voltage is applied, you will get the current through the circuit, right? In that perspective, this IT, that means the basically the charge. So charge is the output here. What is the output here? Your output is equal to charge Q. So you see, d square dt square, this is charge Q, d square dt square, this is x, this is d dt of x, this is d dt of Q, this is k into x, this is 1 by c into k, right? So if these are the two differential equations corresponding to the mechanical system and electrical system, but you get the similarity between the all the quantities corresponding to that. What are these? This is m, this is l, this is b, this is r, this is k, this is, you can write it 1 upon c. So this is 1 upon c. So in case of force voltage analogy, then I can write that in case of force voltage analogy, the mass of the body in mechanical system corresponding to the inductor, and damping coefficient in the mechanical system corresponds to the resistance, and spring constant in the mechanical system corresponding to 1 upon capacitors in the electrical circuit. So I can just simply write the analogy between the parameters. So what is the analogy we are talking about? Force voltage analogy, right? This is, we can talk it as force voltage analogy, and M equivalent to L, B equivalent to R, and AC K equivalent to 1 by C, right? That means normally this kind of analogous system is required in control system for any electrical engineer, because there are certain devices, and many devices are there in the industry which are modeled with the mechanical system. Now, in order to check the functionality, some kind of simulations are to be done using MATLAB, PSPICE, PCM, Multisim, whatever the different tools are available by the electrical engineers. And what happens when these electrical engineers are going to model this system, that means if this system is to be checked, first of all, for any system, you see, this is your system, how it is checked. One kind of input is applied and one set of output is obtained. So if the system is known to you, then any kind of input that I will discuss in the later classes, what are the different inputs, standard inputs are available. These standard inputs are applied and corresponding to outputs are obtained in lab itself. So so to model this mechanical system is not so easy in the laboratory. So corresponding to that, if you can get the electrical modeling of the system, then same kind of input is applied and the output is obtained. That means the system can be checked easily. That is why this kind of analogous system has been developed, and electrical networks corresponding to the mechanical circuits or mechanical networks are actually developed, right, by using this. So so far we have discussed about the force voltage. Now I have to write the equations for the force current analogy. So for force current analogy, we have to get the parallel RLC circuit, right? So mechanical system will remain same. Corresponding to that, one electrical system. This is for parallel. You can write the parallel RLC circuit. Right? If you write the parallel RLC circuit equations, then definitely current is playing the main role. That is, forcing function is current here. You can now relate why these names are given like this. This is R, this is L, and this is C, right? These are the nodes. So how this circuit is analogous to this? That is very simple. You see what happens here. Again, you have to write the node analysis. That means here you have to do the KCL analysis. That means Kirchhoff's current law. And once you go through this Kirchhoff's current law, then we will get the similar kind of actually expression in uh, terms of its differential equations. And definitely you see this is IT is the amount of current which is used to actually this is a function the system, that means this is the forcing function here, and you see definitely this will be I, right? So that is why this is known as the force current analogy. Previously it was the force voltage analogy, now it will give you the force current analogy, how it gives you the current voltage current force current analogy, that I will discuss here. So first of all, this is KCL. That means amount of current is IR, amount of current is say IL, and amount of current is say IC, right? So what is the first equation we can write it is at IT equal to, or you may simple ignore the tan T, IR plus IL plus IC. So you see these three are parallel paths, right? So if these three are parallel paths, then what is the voltage across capacitor? That will be equal to the voltage across inductor, that will be the voltage across the resistance R, right? So if we can find that this voltage across the capacitor, then definitely you can find out the rest of the voltage, and corresponding to that you can get the actually node equation satisfactions. That means the value of IR IL I have seen such that this will be equal to I. That is our motto. So uh, you can see the voltage across the capacitance for the analysis of it as VC. So VC is the voltage across capacitor C. Now again you see the concept of flux here. When the current change, the flux generated, that means say phi is equal to your phi, and you see this change of phi is the development of the EMF, that is the voltage across the capacitance C, you can see, or you can say this is the voltage across the resistance R, across the inductor L. So what happens, this VC is equal to R d phi dt, or you can say this VC into dt integration is equal to d phi, or this phi d phi integration of d phi means phi is equal to basically VC dt. This is one expression required for our analysis. Second one is that the voltage across this inductor, voltage across the inductor is given by say L, so DIL dt, right? So L DIL dt is the voltage across the inductor, that is again equal to your VC, right? You see from here L DIL integration of it is equal to VC dt. And what is the value of VC dt? VC dt is equal to your phi, right? So this part is equal to your flux phi. So L DIL integration of DIL means IL. So IL into L equal to your phi. So here you will get the current through the inductor part is phi by L. So that is one expression we will be required here. And second thing is that, so voltage across resistance, that is VC by R. VC by R, that is the VC is the voltage across the resistance. So what is the current passing through it? That is your IR. So IR is equal to VC by R. Again VC equal to, you see, d phi dt. So we can write it that 1 by R d phi dt. So you get IR and we get IL. Now we have to get the value of IC. What is the value of IC? You see, IC dt integration 1 by C, that is equal to your VC, right? That expression we know that VC is equal to 1 by C integration of IC dt. See, so here you see integration of IC dt is equal to C into VC, right? And from here you can get C VC dt is equal to your IC. So IC equal to C dVC dt, right? So you see this IC is equal to C dVCC dt. So we get IC is equal to C dVC dt. See, so IC can be written like in terms of phi. Say dVC dt. You see from here we'll get dVC dt is equal to d2 phi dt square. Right. So IC will be equal to here. IC is equal to C d2 phi dt square. So we get three values. One is IL, that is phi by L. One is IR, that is BC by R, that is 1 by R d phi dt. Because all are in terms of phi, we are setting at the flux. That is because there is changing current I, so we can get the flux developed in the circuit, and that flux is, again IC is nothing but change of rate of flux is giving you the voltage. So VC is equal to dVC dt, and one by one we can get, say again I repeat, this is the voltage across, this is VC, this is voltage across the inductor VC, voltage across the capacitors is again VC. So VC by R is equal to IR. So VC by R means 1 by R d phi dt. So this is the expression for the IR. Next we can get that L dIL dt, that is the voltage across the inductor, that is again VC. So L dIL dt, if you integrate on both sides, L integration of dIL is equal to VC dt, and integration of the VC dt from this expression, you see this is your phi, integration of VC dt is phi. So integration of dIL, that is total inductor current, L into IL is equal to phi, so IL will be given phi by L. Similarly 1 by C integration of I dt is equal to VC. So if you integrate on both sides, and ultimately differentiation of this part will give you IC, and this is dVC dt. So dVC dt means again d square phi dt square. So these are the three values of the IR, IC and IL you will get, and corresponding to that we can write the expression for I. Here we can write directly, we can just, this is I, and IR. What is the value of IR? IR is equal to 1 by R d phi dt plus 6. What is the value of IL? IL is phi by L, so 1 by L phi plus, we can write IC is equal to C dVC dt. So C dVC dt means IC is equal to C d square phi dt square. So we can write it as C d square phi dt square. Now these are the two expressions. You see, this is a parallel RLC circuit consisting of the three elements again, RL and C. So this is the force current analogy, and see, this is your mathematical equations for the mechanical system corresponding to this mass, spring and damper, and this is the equation for the parallel RLC circuit. But you can see the similarity. What is the similarity? You see this d square x dt square. Here output is phi, and input I is the input and phi is the output corresponding to this system, right? Once you know this, the phi, so you see the equilibrium, the analogy, M and C. This is M, mass corresponding to capacitance, and this X corresponding to phi. This is B. B is equivalent to 1 by R, and K is equivalent to 1 by L, right? So that means in case of you see this force current analogy, what are the different equilibrium? That means the quantities which are analogous to each other. I can just write here to make a clear concept. So what is this? M corresponding to mechanical system equivalent to C, and say B is equivalent to 1 by R, and K is equivalent to 1 by L. This is for force current analogy, right? So we get the two analogous system. One is force voltage analogous system, one is force current analogous system. So, and the relation between these variables M, B and K with respect to R, L and C, right? And next class, next lecture video, we will discuss a few examples and how to get how to draw the equivalent circuit from a given mechanical network. That means a mechanical system will be given like this, and corresponding to that you have to write the electrical system network, right? So that is some procedure that I will discuss in the next lecture. Okay.